How intensely would an oil tanker in the Strait of Hormuz burn if it were hit by an Iranian missile? That's what Trump is afraid of. Watch the video until the end to see what happens when a ship loaded with hundreds of thousands of tons of oil is attacked with a missile. We're going to talk to you about the explosion, the fire, the marine pollution, and finally about what I think scares Trump: fluctuations in oil prices and the prestige of the American military. There is a place on the map, only a few dozen kilometers wide, through which a huge part of the energy of the modern world passes. It's called the Strait of Hormuz. In 2024, an average of about 20 million barrels of oil per day passed through this strait, which is around 20% of the global petroleum fuel consumption. The size of the oil tankers that transport this oil is hard to imagine. A VLCC-type supertanker, which means very large crude carrier, is over 300 meters long, almost as long as 3 football fields placed end to end. It can carry up to 2 million barrels of oil, which is about 300,000 tons of hydrocarbons. Basically, it's a floating city filled with chemical energy, and that's exactly why the obvious question arises. What happens if such a tanker is hit by a missile? In the movies, the answer is simple: a giant, instant, spectacular explosion. The answer in reality is much more complex, and in a certain sense much more frightening. The first counterintuitive fact is this: crude oil doesn't just explode like dynamite. In fact, crude oil is relatively hard to explode. If you threw a lit torch into a tank of crude oil, in many cases you wouldn't get an explosion, but rather a slow burn on the surface. This can be seen in the images of the oil fields at Maikop, the ones briefly captured by the Germans in World War II. The Soviets burned them to keep them from the Germans. The reason for the slow burning is as follows. Burning needs fuel, but it also needs oxygen. The oxygen in the air can't penetrate efficiently into the compact mass of liquid, so the liquid oil itself doesn't burn everywhere at the same time. It burns mostly on the surface, where it comes into contact with the air. So what actually explodes? The vapors. The oil evaporates, especially its lighter components. Even in an apparently full tank, there's a space above the liquid filled with hydrocarbon vapors. These vapors, mixed with air, can become much more dangerous than the liquid itself. In fact, this is the principle we use every day in a car engine. A car doesn't burn liquid gasoline the way a puddle of fuel burns. A mixture of air and gasoline vapor enters the combustion chamber. The piston compresses this mixture, the spark plug ignites it, and the hot gases expand and push the piston down. This is how we obtain mechanical work. In a gasoline engine, this process is controlled. In the Otto cycle, we have intake, compression, combustion, and exhaust. Everything happens in a small volume, at the right moment, with a mixture of air and fuel vapor that is as precisely metered as possible. Here, a fundamental concept in combustion appears: the flammability range. Fuel vapors can only burn within a certain concentration range. Too little fuel prevents combustion from spreading. If you have too much fuel and too little oxygen, the reaction gets choked, but if the ratio is right, the mixture ignites violently. In the car engine, this ratio is controlled. But what happens if a rocket hits an oil tank and suddenly creates a cloud of vapor and fine droplets mixed with air? Then we're not talking about an engine anymore, we're talking about a dangerous explosion. Imagine the following scenario. In the Strait of Hormuz, an Iranian missile hits a side tank of a supertanker. The impact breaks through the metal walls and sprays the oil, turning it from a dense liquid into a fine aerosol with clouds of microscopic particles and vapors mixed with air. What has changed? Well, the surface area between the fuel and oxygen has increased exponentially. Instead of burning slowly on the surface of the liquid oil, the chemical reaction can quickly engulf a cloud of vapor and fine droplets mixed with air. This is what engineers call a fuel-air explosion. Chemically speaking, the reaction is relatively simple. The carbon from oil, which mostly comes from ancient decayed marine organisms, plus the oxygen from the air, produces carbon dioxide. The hydrogen in oil, which comes from the same organic molecules plus oxygen, produces water, but the energy released in a fraction of a second is immense. The temperature reaches about 1000 to 1500 degrees Celsius. The resulting gases expand violently, creating a shock wave. And how does an oil tanker explode? Most oil tanker explosions are not detonations. That category of explosion is specific to things like TNT, in which the shockwave propagates supersonically and matter is destroyed almost instantly. Oil tank explosions are usually fast burns in which the flame propagates at a lower speed. They are slower in principle, but no less destructive when the volume involved is large enough. The problem is amplified when the fuel is stored in metal tanks. In the case of pressure vessels containing superheated liquids or liquefied gases, a phenomenon called BLEVE can occur, which stands for Boiling Liquid Expanding Vapor Explosion. Here, a fuel tank is exposed to an external fire. The liquid inside gradually heats up. The walls hold, and the liquid fuel remains in a liquid state, even at temperatures far above its normal boiling point. This is called superheating, but if at some point the tank wall fails, either due to thermal corrosion or impact, then the pressure drops instantly, because a breach is created through which the accumulated pressure is released. At that moment, when the internal pressure suddenly drops, the superheated liquid begins to boil explosively in a short period of time. As the oil boils, it evaporates and its vapor volume can suddenly increase by hundreds of times. The tank turns into a superheated vapor bomb. Eventually, all the tank's walls collapse. The result? A fireball tens of meters in diameter, depending on the tank, metal fragments projected at hundreds of meters per second, and a pressure wave that hits everything around. A similar, though not identical example is the explosion at Buncefield in the United Kingdom in 2005. There it was an explosion caused by a large fuel vapor cloud. The shock wave was so powerful that it was detected by seismic networks. However, in the case of crude oil from a tanker, the more likely scenario is a combination of a tank fire, flammable vapor, local explosions, and burning oil spill. How resistant are modern oil tankers if they are attacked by Iranian missiles in the Strait of Hormuz? In 1989, the Exxon Valdez incident occurred, one of the most well-known oil disasters in history. The oil tanker ran aground in Alaska and the spilled oil caused a huge ecological disaster. Even though it wasn't a military attack, the incident showed how vulnerable oil tankers can be when the walls of their tanks are damaged. Since then, the shipping industry has increasingly adopted the double hull standard. Thus, there are two layers of steel between the water and the oil tanks. The tanks are compartmentalized, so a single hit does not automatically sink the ship. That's why, in an attack, sinking is not necessarily seen as the first or only danger. The immediate problem could be fire. A ship's steel can lose its mechanical strength at high temperatures. Pipes fail, nearby tanks heat up, and chain reactions occur. And in this way, an oil tanker can burn for days, sometimes even weeks, without suddenly exploding all at once and then sinking. A famous case is that of the Iranian supertanker Karp 5. The ship had been damaged during the Iran-Iraq War, and in 1989 it suffered a serious accident in the Atlantic off the coast of Morocco with an explosion, fire, and a massive oil spill. The fire was quickly brought under control, but the oil continued to leak for about 12 days. The major problem with an attack on an oil tanker in the Strait of Hormuz by Iranian missiles is not the explosion, but what follows. If the tanks break completely, an even bigger disaster follows, an environmental one. The oil spilled into the sea doesn't disappear. On the contrary, it behaves like a complex and extremely persistent chemical system. Why? Because oil is lighter than water, it floats and spreads quickly. A single liter can cover thousands of square meters with a thin film. A modern oil tanker carries hundreds of millions of liters. After the oil reaches the sea, the evaporation of the compounds in the oil begins. Compounds like benzene or toluene rise into the atmosphere, the air becomes toxic, and the impact on the ecosystems around the coasts is immediate. After a while, mostly the heavy fractions of the oil remain. Some can form emulsions, stick to sediments, and reach coastal areas where they persist for a long time. In this way, the oil film on the surface can reduce the gas exchange between the ocean and the atmosphere, partially block the light, and affect the phytoplankton, which is the source of almost half of the planet's oxygen. The disaster that followed the Exxon Valdez accident in 1989 shows us that some areas need decades for complete ecological recovery. What is really at stake in a tanker explosion in the Strait of Hormuz? Why am I not risking anything? Not just because of the lost money. A simple calculation shows that you can lose, with just a single medium-sized oil tanker, hundreds of millions of dollars if you add up the value of the ship, the cargo, and the costs of salvage operations. But the problem isn't the money, it's the economic mechanism that kicks in immediately. Insurance companies will immediately raise the cost for ships in the region. Ship owners can reroute voyages, avoiding the strait for a long period of time. Shipments slow down, global supply is disrupted, the price of a barrel of oil rises sharply, and the stock markets may panic again. The fear is not about the explosion itself. The fear is about what comes next, a fluctuation in energy prices that can destabilize entire economies. I think Trump is afraid of losing control over the economic and political narrative. Some might interpret a successful Iranian attack on the tankers as a demonstration of America's weakening military power. That's how we went from hydrocarbon vapor physics and combustion chemistry to economics. We might be afraid of the size of the explosion, or maybe we're afraid of the environmental consequences. Trump is afraid of the economic and political ones. This was today's video. If you also think what I do is useful, you can support me on Patreon. There, I can answer your personal science questions directly through a personal video that I send you on WhatsApp. If you haven't subscribed to the channel yet, you can do it right now by pressing this button. Until next time, I'm Christian Presura, Fisica Povestita. You are cool. All the best. Goodbye.